Students, myself, Virendra Kumar Maurya, Associate Professor, Department of Electrical Engineering, School of Engineering, Babu Banarsi Das University, Lucknow. I welcome all of you in this video lecture. Please see this lecture thoroughly from beginning to end. Now please see the board. This is the picture of great scientist Nikola Tesla. Discovery of induction motor goes to in his credit. This is the diagram of three-phase induction motor. Now the definition of motor. Electrical motor is a machine which converts electrical energy into the mechanical energy. Now see the induction motor. There are two main parts. One is stator and other one is rotor. Now I am going to discuss these parts one by one. See the first one, that is stator. Stator consists of a steel frame which encloses a hollow cylindrical core made up of silicon steel material. We use this material as a core because it reduces the hysteresis and eddy current losses. Slots are made on the inner periphery of the laminated core. Insulated conductors are placed in these slots and are connected in the form of star or delta. Finally, it is called as stator winding. The three-phase stator winding is wound for a definite number of poles as per the requirement of the speed of the motor. Three-phase supply is given to this winding. When three-phase current passes through this winding, something very interesting happens. It produces a rotating magnetic field. This rotating magnetic field passes through the rotor. What will happen by this field and what is the effect of this field on the rotor? We will discuss it later. Before that, listen about the second component, that is rotor. There are so many types of rotors. Some of them are given over here. Number 1, cylindrical rotor. 2, salient pole rotor. 3, wound rotor or slip ring rotor. These rotors are used generally in synchronous machines. And the fourth one is squirrel cage rotor. Squirrel cage rotor is used in induction machines. It consists of a laminated cylindrical core having parallel slots on its outer periphery. One copper or aluminum bar is placed in each slot. All these bars are joined at each end by metallic rings called end rings. This forms a permanently short-circuited winding. These bars are little skewed due to the following reasons. Number 1, hum and noise reduction. Second, stalling of motor. The entire construction resembles a squirrel cage and hence the name. Now the working of three-phase induction motor. When three-phase supply is given to the motor, the resulting current generates the flux phi. Due to the switching sequence of three-phase supply, that is R by V, there is a rotating magnetic field which rotates around the rotor conductors. According to the Faraday's law, which states that an EMF is induced in a closed circuit due to the change in magnetic flux through the circuit. An EMF is induced due to this current flow in the rotor conductor. Direction of current is given according to the Lenz's law. Hence, the rotor rotates in the same direction to reduce the cause, that is, relative velocity, thus rotating the rotor of induction motor. Therefore, in this process, poles are induced on the surface of rotor, and these poles always tries to catch the opposite poles which are rotating on the inner periphery of the stator. Thus, rotor rotates in the direction of rotating magnetic flux. Rotor poles always try to catch the rotating poles on the stator frame, but they cannot achieve the same speed, because if the rotor rotates with the same speed, then there will be no relative motion between stator poles and rotor poles, and hence there is no change in the flux experienced by the rotor, and in that case EMF induced in the rotor conductors will be zero. Therefore, rotor always rotates in less speed than the speed of the rotating flux. This process continues until the supply is given to the stator winding. Speed of the rotating magnetic field is known as synchronous speed. Now listen regarding the concept of slip. The difference between the synchronous speed of the rotating stator field and the actual rotor speed is called slip. Generally, it is expressed in percentage. In an induction motor, the change in slip from no load to full load is hardly 0.1% to 3%. Therefore, a three-phase induction motor is essentially a constant speed motor. So, in this way, induction motor will work. Now, I am going to discuss regarding the starting torque of three-phase induction motor. There are two types of motors. Number one, squirrel cage motors. Second one, bone rotor motor. Now, see the first one, that is squirrel cage motors. Rotor bars are permanently short-circuited in induction motors. It is not possible to add any external resistance in the rotor circuit at starting. Consequently, the starting torque of such motors is low. Squirrel cage motors have a starting torque of 1.5 to 2 times of full load value, with a starting current of 5 to 9 times of full load current. Now see the second case, that is bone rotor motors. The resistance of the rotor circuit of such motors can be increased through the addition of external resistance. By increasing the proper value of external resistance, that is R is equal to X, maximum starting torque can be obtained. As the motor accelerates, the external resistance is generally cut out until the rotor circuit is short-circuited on itself for running conditions. Now the next question is, why is the air gap in between rotor and stator of a three-phase induction motor kept as small as possible? The air gap between the rotor and stator of a three-phase induction motor is made as small as possible due to the following reasons. Number one, mutual flux may be produced with a minimum exciting current. Second, leakage reactances are as small as possible. The next question is, what are the advantages of bone rotor motors over squirrel cage motors? Bone rotor motors have the following advantages over squirrel cage motors. The first advantage is high starting torque. Second, low starting current. Third, smooth acceleration under heavy load. Fourth, no abnormal heating. Fifth, good running characteristics. And the sixth one is adjustable speed. These are the advantages of wound rotor motors over squirrel cage motors. Now the numerical problems related to the three-phase induction motor. Number 1. A 500 horsepower three-phase 440 volt 50 Hz induction motor has a speed of 950 rpm on full load. The machine has 6 poles. Calculate the full load slip of the machine. Now see the solution. According to the question, 500 horsepower 3-phase 440 volt 50 Hz induction motor is running at a speed of 950 rpm. This is the speed of motor at full load. So it is N. Number of poles of the machine 6. Calculate slip. First of all, I am going to calculate synchronous speed, that is 120 F divided by P. 120 F is 50. Number of poles are 6 is 1000 rpm. Now for the slip, that is ns minus n divided by ns into 100. So it is 1000 minus 950 divided by 1000 into 100. That is 50 into 100 divided by 1000. So the value of the slip is 5%. Now the second numerical, a 3-phase 440 volt 50 Hz 8 pole induction motor. Find the actual speed of the motor if the slip is 2.5%. According to the question, induction motor having number of poles 8, 50 Hz and slip is given to you 2.5%. Calculate actual speed of motor. Right? First of all, I am going to calculate synchronous speed, that is ns 120 F divided by P. 120 F is the frequency, that is 50 Hz divided by number of poles, that is 8. After the calculation, it is 750 rpm. Formula of slip, that is S is equal to ns minus n divided by ns into 100. 2.5 is equal to 750 minus n divided by 750 into 100. After the cross multiplication, we can calculate the value n, that is the actual speed of motor. It is 731.25 rpm. Right? So according to the question, after the calculation, actual speed of motor is 731.25. So this is all about the three-phase induction motor in theory and numerical as well. Thank you very much.